All right, this is Unit 7, Lesson 1, Part 1, and we're going to be introducing exponential parent functions, kind of starting off slow on this first day, just looking at parent functions before we make any sort of transformations to them, which will come in the next lesson in Part 2. So a couple quick little definitions. The exponential parent function looks like this. So we always start with f of x for all of our functions is equal to b to the x. So b is a number. It could be 3 to the x, it could be 1/2 to the x. So we're going to talk about what they'll look like based on different values that b could take on. So if b is greater than 1, the function is an exponential growth which means it is increasing. Okay, so you'll see this shape that kind of like drags along here and then just shoots up really fast as it moves to the right. That's what exponential growth looks like. If b is something less than 1, so I'm hesitant to say fractions because fractions aren't always less than 1, but if you have like 1/2, 1/3, 2/3, something like that, then that makes the function an exponential decay. That's what we call that, which means that the function is decreasing. So those ones kind of start off really steep and then just like level out as they move towards the axis. So each of these graphs, like I said, they kind of level out and just drag along like this, and the other one drags along like this and then shoots up. That's because it has an asymptote along the x-axis. And an asymptote is a line which the graph gets extremely close to at the ends of the graph. So you'll see what that means once you actually see an asymptote at play. One of the definitions is that it's a line that the graph gets really close to but never crosses, and that's not technically always true, so I don't want to give you guys that part of the definition. So number 1, f of x equals 2 to the x. As we've done with many other types of functions, if we don't know what the function looks like, we set up a table, we plug in different x values, and then we can plot them. So we are going to set up an xy table, and the values that we're going to stick with for these graphs are -2 to +2. And that's enough to give us just a good picture of what these graphs are going to look like. So when I take 2 and raise it to the -2nd power, so I'll kind of write all this out first. 2 to the -2nd power. From our last unit, you remember some different exponent properties. So negative exponent means that we flip down to the denominator. So this is the reciprocal of 2 squared, or the reciprocal of 4. So we get 1/4. This one, 2 to the -1st power, would be the reciprocal of 2 to the 1st power, which is 1/2. You can also always feel free to just plug these into your calculator. This one, 2 to the 0, anything raised to the 0 is 1. 2 to the 1st is 2, and 2 to the 2nd is 4. So we have just these 5 points to work with, but it's going to be enough to see the general pattern. So -2 and then 1/4 is just like a tiny little decimal right there. -1 1/2 is a decimal, but a little bit higher. 0 1 is right here. 1 2 is right here, and then 1 4 is right here. So you can see along the left-hand side, if I were to keep, because this is, as I go this way, I'm multiplying by 2, and as I go this way, I'm cutting the numbers in half. So if I were to keep cutting the numbers in half, I would have 1/8, 1/16, 1/32, 1/64, and all that's going to do is it's going to bring it really, really close to 0. So on this end, it gets really close to 0, but it never actually goes negative. And then here, it just gets really large really quickly. Because if I continue this pattern and I keep doubling, it goes 8, 16, 32, 64. It gets really large really quickly, which is why this gets practically vertical and this gets practically horizontal. All right, so the first one always takes the most explaining. So let's look over here at our characteristics of these functions. We've worked with these before, but not with this specific type. So our domain. Domain is always the x-coordinates. It's what you're allowed to plug into the function. You can plug any number in here that you want. So our domain is all real. So you're allowed to work with any x value that you want. The range told you this is kind of like a cutoff point here. No matter how far you go this way, if you keep cutting numbers in half, they're just going to get closer and closer and closer to zero. They're never actually going to be negative. Because if you keep cutting something in half, it's not going to mysteriously become negative. It's just going to get smaller. So our range is only values that are greater than zero. Not greater than or equal to, because it will never actually hit. It'll just get very, very close. End behavior. As x approaches infinity, so this is the right edge of the graph, as we move to the right this way, the graph just shoots up. So our function values are going up and up and up. So we say infinity for that. And we've worked with this before, just like I said, different types of functions. And then as x approaches negative infinity, so that's the left end of the graph, as we move from right to left and go this way, my function values are just getting closer and closer to zero. They're not going down, they're not going up, they're just getting closer and closer to zero. So that's what we say here. My y-intercept is where it crosses this y-axis right here, and that is this point. That is the point 0, 1. And then my asymptote is the value that my graph is approaching, but here isn't actually ever going to reach. And that would be the horizontal line, y equals 0. All right, so for today's notes, because we're not making any changes, because we're not moving anything up, down, left or right, because we're not doing any stretching or compressing or flipping, all of these things are going to remain the same for all the different graphs that we're going to look at. All right, so number two is 3 to the x instead of 2 to the x. So we can set up this same xy table. We'll use these same 5x coordinates. It's going to be the same for all of our tables. And then this time we're raising them to the third, or on the base of 3. So 3 to the negative second is the reciprocal of 3 to the second. So that'd be a 1/9. 3 squared is 9, right? 3 to the negative first is the reciprocal of 3. So 1/3. 0, 3 to the 0 is 1. Everything to the 0 is 1. 3 to the first is 3, and 3 to the second is 9. So as we move down our table this way, the values are getting multiplied by 3, right? Times 3, times 3, times 3. As we move this way, we're dividing by 3, or multiplying by 1/3. All right, so we can work it backwards. Same thing as this. We were either cutting in half or multiplying by 2. These ones were cutting in thirds or multiplying by 3. So plot these points. So -2, 1/9, that is barely off the x-axis here. -1, 1/3, 0, 1, 1, 3, and then 2, 9. So these ones, because the 3 is bigger than the 2, these ones are gonna grow even more quickly to the right, and they're gonna shrink down to 0 even more quickly to the left. Because if I keep cutting this into thirds, it'd be 1/27, 1/81. If I keep multiplying by 3, I get 27, 81, so it gets much larger, much more quickly. But the general behavior is still the exact same. It still just gets closer and closer to 0. It still just shoots up really quickly as we move to the right. So all this stuff is going to be the exact same. Domain is still all reals because I can plug in anything I want. Range is still y is greater than 0 because we're never going to cross below this line. We're never going to become negative. As x approaches infinity, f of x approaches infinity because the right end of the graph just shoots upwards. As x approaches negative infinity, f of x approaches 0 because as we move to the left here, we're just getting closer and closer to a value of 0. The y-intercept is still the same because if I plug in 0 for x, I still get 1 for y no matter what my base is. And the asymptote is still y equals 0 because I didn't shift my graph, which means they're all just getting closer and closer to 0. So these will be the exact same. So I'll kind of explain them less and less as I go through these problems. Next, number 3, now we have a 1/2 as a base, which is something smaller than 1, so you're going to see how that plays out and what the graph looks like. So same exact table here, same 5 values that we just did with the first 2. So now 1/2 to the negative second. Okay, remember the negative flips it, and then the 2 squares it. So if I flip this, the 1/2 becomes 2, and if I square it, 2 squared becomes 4. So the negative exponent, remember, is what flips this. So if I use -1 as my exponent, the negative flips this to 2, and then the first power means it's just 2. 0, 1/2 to the 0 is 1. 1/2 to the first is just 1/2. And 1/2 squared, 1/2 times 1/2 would be 1/4. So in this one, I've got like the exact opposite table as I had with number 1. So this time as I go down the table, my numbers are getting cut in half. And as I go up the table, my numbers are doubling. So let's see what that looks like on a graph. So negative 2, 4, negative 1, 2, 0, 1, 1, 1/2, and then 2, 1/4. So I'm going to compare. This is the one that we just did. We had just the opposite values here. And so this is like a mirror image of what I'm going to have. So this one is my first example of exponential decay. So this time to the left, it gets really, really super steep. And then to the right, when these values just keep getting cut in half, 1/8, 1/16, 1/32, this is just going to get really close to 0. And this side is going to get really, really steep. So everything that I write in this box over to the right is going to be very, very similar, but I'll show you some key differences. So domain is still all rails because I can plug in anything I want. Range is still y is greater than or equal to 0. So you have this kind of boundary right here. This is what's going to swap, is the end behavior when I'm dealing with decay instead of growth. This time, as x approaches infinity, so remember that's the right edge of the graph, as I move off to the right, now this one is just dragging along at a value of 0. So it swaps from what I had on the front page. And then this time as x goes to the left, as I move to the left, the graph just goes up and up and up. So that would be positive infinity. Y-intercept is still the same. I still have 0, 1, because if I plug in 0, I'm always going to get 1. And my asymptote is still the same. All right, let's look at another, number 4. Okay, same 5 x values. Negative 2. Negative means I flip it. So 2/3 becomes 3/2, and I square it. So when I square 3/2, I get 9/4. And 9/4, just so you see the decimal, is 2.25. Negative 1. Negative 1 means I just flip it. So 3/2, and that's 1.5. 0, if I raise to the 0 power, I get 1 every time. If I raise the first power, I get 2/3. And if you want that in fraction form, that'd be 0.6 repeating. And then 2, if I square it, 2/3 becomes 4/9, and that is 0.4 repeating if you were to plug that in. So 5 points to plot here, negative 2 and negative 2.25, it's a little higher than 2, negative 1 and negative 1.5, 0, 1, 1 and that's 2/3, and then 2 4/9, just a little bit below a half. So this one, 2/3 is pretty close to 1. So the closer the base is to 1, the less like dramatic the growth or decay is going to look. So this one is actually like kind of stretched out compared to the original, but it's still going to just drag along 0 here. That part will never change. So this is much more steep because this is farther away from 1. This base is closer to 1, so it's going to be more level. Domain is still all rails. Range is still y is greater than 0. This end behavior now matches this end behavior. The right arrow is just dragging along this asymptote here at 0. The left arrow is going up and up. The y-intercept is still 0, 1, just like all of these have been, and the asymptote is still this line right here, y = 0. All right, one last one, a base of 5/2. So remember, like I said at the beginning, 5/2, of course, is a fraction, but it's 2.5, which is bigger than 1. So it's going to be growth rather than decay. So don't get in the mindset of thinking that all fractions will be decay. It just depends how big the fractions are. All right, negative 2 means I flip and square. The negative means flip, the 2 means we square it. So flip first, and I get 2/5, and then square 2/5, and I get 4/25. And 4/25 is 0.16. Negative 1. Negative means flip. The 1 means it stays the same. So 5/2 becomes 2/5, which is 0.4. Anything to the 0 power is 1. Raising to the first power stays the same. So I get 5/2, which is 2.5. And finally, squaring 5/2 becomes 25/4. And that is 6.25. So 5 values. Negative 2 and 0.16 is like barely bigger than 0. Negative 1 and 0.4 would be just about a half. 0, 1. 1 and 2.5. And 2 and 6.25. Good. So this is farther away from 0, so it's going to be steeper. And it's actually 2.5 is obviously halfway between 2 and 3. So if you look, kind of a comparison here between these two. So here's 2. Here's 3, which gets much steeper, much faster. This is kind of right in between the two because it's 2.5. So that's what the graph looks like. Domain is still all reals. Range is still greater than 0. This end behavior switches back again. The right arrow is the one that's going up to infinity, and the left arrow is the one that's dragging along towards 0. Y-intercept is still 0, 1 for all of these today, and the asymptote is still y equals 0. So just kind of an intro before we make any transformations or anything in the next part.